Okay, let's look at this example. The probability that a patient recovers from a rare blood disease is 0.4. If 15 people are known to have contracted the disease, find the probability that in part 1, exactly 5 survive. Right, so for us to find the probability, okay, we need to decide on or determine, okay, what distribution this follows. Right, so we look at this part here. Okay, how do you know if binomial distribution is a suitable model for a random variable? Okay, for you to solve this question, okay, you need to first do two things. First is you need to define, okay, what is the random variable denoting the event. Then the second thing is, okay, you need to check if the random variable satisfies the 4 conditions for the binomial model. Right, so in part 1, okay, we want to find the probability that exactly 5 survive. Okay, so what is the number of trials and what is the case of success? Okay, because we are looking at exactly 5 survive, we are looking at the number of patients who survive. Right, so you define X as the random variable denoting the number of patients who survive. Right, then in the next step, step 2, we are checking whether it satisfies a binomial model. Right, so the first condition says that the experiment consists of a finite number of repeated trials. Right, in this case, we have 15 patients, we have 15 repeated trials. Right, for the second condition, right, we are looking at whether each trial results in 2 mutually exclusive outcomes. So in this case, a patient either survives or does not survive, okay, which is also satisfied. Right, in the third condition, we want to know whether the probability of success is constant for each trial. Right, based on the question, the probability of a patient surviving is constant at 0.4. Okay, the same for each patient. So this condition is also met. Right, in the last condition, correct, the trials are independent of one another. So are they? Right, so the outcome of a patient, whether it survives, is independent of the outcome of other patient. Okay, hence X does follow a binomial distribution. Based on the earlier discussion, okay, we know that binomial model is a suitable model for the random variable. Right, so how do we define the random variable for a binomial distribution? Right, so if you look here, okay, the binomial random variable is always defined as the number of something out of something. Right, so in this case, we will let X, okay, be the random variable denoting the, okay, so we are looking at the number of patients who survive, okay, but it is out of how many, right? So you write the number of patients who survive. Okay, out of 15 people. X follows a binomial. Okay, so what's the number of trials? You're looking at 15 people, so your n is 15. Then what is the probability of success? Okay, so we're looking at the patients who survive. Okay, patients who survive is given by 0.4. Right, so in part 1, you're looking at exactly 5 people survive. Okay, exactly 5 survive. Right, so we are using binomial PDF. Right, you key in your number of trials, which is n, as 15. Okay, probability of success as 0.4, and the value of x as 5. Right, and from GC, you get this value here. You present answers to 3 SF. Okay, in part 2, we are looking at least 2 patients survive, okay, which can be represented as, in this probability statement, probability of your random variable x greater than or equal to 2, because at least 2 survives includes 2. Okay, so how do you write it in the form that you need to key in to GC? Okay, because GC requires you to enter the value and it is included in the calculation. So because GC requires you to enter in the form of less than or equal to sign, right, we need to convert this to less than or equal to. Right, for you to do that, we will take 1, okay, minus the complement. Right, so if my x is greater than or equal to 2, what is the complement of that? Right, so it will be x get less than or equal to 1. Right, so in GC, you just key in 1 minus, okay, followed by your binomial distribution. Okay, your binomial distribution, which is binomial CDF, okay, because you're looking at, okay, less than or equal to 1. Right, you key in the values of your parameter and the value of x as required. 3, we are looking at more than 9 survive but less than 13 survive. Right, so in this part, okay, more than 9 means my x can take 10, 11. So it includes 10 because 10 is more than 9. Right, in the next part, less than 13, so x can take 12 because 12 is less than 13. Right, but how do we write an equivalent statement so that we can key into GC? Because GC requires us to write it as probability that x is less than something, okay, less than or equal to something. Right, so we know that x is less than or equal to 12, so we know that the probability that x to take should be less than or equal to 12. So what are we subtracting? Right, so we're subtracting away probability of x, okay, less than or equal to something. Okay, so what is that something? Right, so if you look at the number line, right, these are the values that you can take: 12, 11, 10, 9, 8. Right, we want the values from 10, 11, and 12. Okay, this one, 10, 11, and 12. We want the values here. Okay, but we have already also added 9 and 8 and so on. Okay, because you're summing your probability of x, okay, less than or equal to 12. Okay, so we need to subtract away the values that is that's divided between 9 and 10. Right, so we want to extract or exclude rather, okay, these values here. Right, so we want to subtract away probability of x less than or equal to 9. Right, so we key into GC, okay, the two values for x taken a value of 12 and less, right, or the next value 9. Okay, we take the difference and find the difference and write down your answer. For part 4, we are looking at most half of them survive. Correct, so we have 15 patients, so half of them will be 7.5, 15 over 2. So at most half means less than or equal to 7.5. Right? Okay, so we write this as an equivalent statement. Right? Probability your x less than or equal to 7. Okay, then we key in the necessary fields into the GC, okay, to find the answer, which is 0.7868, and we write the answer down as 3 SF. In the last part of this question, we are given that the probability that at most k patients survive the disease is at least 0.8. So how do you represent this in a probability statement? Alright, so first we write probability of something. Okay, so what does at least 0.8 represents here? Okay, this represents the probability, right? Right, so it must be outside the bracket. So this is 0.8. So what does at least mean? Right, so at least means greater than or equal to. Right, so we write here greater than or equal to. Okay, then we try to fill up what is in the bracket. Right, so in the bracket we have the random variable x, which is the number of patients who survive out of 15. Right, so this one says at most k patients survive. Right, so it has to do with k. Right, so this is k. So what is the inequality that connects x and k? So it says here at most. Okay, so at most means less than or equal to k. Right, then next is to key in this into the GC, okay, using your graphical mode. Right, you key in under y1 using binomial CDF with the respective parameters, which is indicated in this table. Then you observe from your table settings. Okay, you run through the list of values and look for the row that has that is close to 0.8. Right, you will be required to write down the three values here that exceeds 0.8 and is less than 0.8. Okay, do take note that in your table headings, you are required to write k here, the values of k, and the probability that x is less than or equal to k. Okay, so from the table, we can see that the least value of k is actually 8. Okay, because the next value of k, when it's 9, okay, it is not the least value, it is the next least value. Okay, for example 3 with unknown n, okay, we are given that the 20% of the population is left-handed. Okay, we are required to find the probability that a group of 8 people contains not more than 3 left-handers. Okay, so first thing is we need to define the random variable x. Right, and the random variable x consists of two parts. One is what is your case of success, and the next part is out of how many trials. Right, so in this case, your case of success is left-handers. Alright, so we will write your random variable x denoting the number of left-handers. Right? And in the next part, okay, we will write out of how many. Right? So this is a group of 8 people. Okay, so we'll write out of 8 people. Right? So then you write down your distribution for x. Okay, so your x follows a binomial distribution. Right? Your n is 8 because out of 8 people, and your case of success, the probability is 20. Okay, so it's 20%. So it convert to probability, it is 0.2. Okay, then in the answering the question, right, it says here, group of 8 people contains not more than 3 left-handers. Right, so you know that it starts with probability of x. Okay, so your x here is number of left-handers. Right, you want not more than 3 left-handers. Right, so you know that this is 3. Right, so not more than would be less than or equal to. Right, so 3 is not more than 3. Right, it is equal to. So it is probability of x less than or equal to 3. Then you press your GC, you should be able to get this value to 3SF. Okay, then let's look at part 2. Okay, part 2 asks you to find the least number of people that should be selected such that the probability that there's at least one left-hander is greater than 0.95. Right, so in this case, because there is a change in the probability, okay, you are looking at the success of probability. You look at the case where at least one left-hander that is greater than 0.95. Okay, so the case is at least one left-hander. Okay, for part 2, you're looking to find the least number of people that should be selected. Okay, such that the probability that there is at least one left-hander is greater than 0.95. Right, so the issue is you do not know what is the number. Right, so you have to define a new random variable. Okay, and the case of success, it is still left-hander. Right, so your new random variable will be let y be the random variable, okay, denoting the number of, okay, so what is the case of success? Right, so I was saying the case of success is left-hander. Right, so it's number of left-handers, okay, from, okay, so the question is, what is the next part? Right, you are looking at out of how many? Right, so we were saying that we are supposed to find the least number of people. Right, so we do not know what is the number of people, so we can let it be n. Okay, so from a group of n people. Right, then you write down your distribution. Right, so then the distribution is now y because you define for random variable y. It follows a binomial distribution with the number of trials to be n people, then followed by your probability of success, in this case, which is left-hander, which is given to be 20%, which is 0.2. Right, since the probability that there is at least one left-hander is greater than 0.95. So how do you look at, how do you write this in a probability statement? Okay, so first thing is, it is probability. Right, so you read the question, it is greater than 0.95. Probability is greater than 0.95. Right, so you know that this is greater than 0.95. Right, so how do you fill this in the bracket then? There is at least one left-hander. Okay, there's at least one left-hander. Right, so your x, or rather in this case is y. Right, your y, it is counting the number of left-handers. Right, you want at least one. So this one will be greater than or equal to 1. Okay, so how do you get to the next step? Okay, because your GC only calculates values less than or equal to. Right, so when you write y greater than or equal to 1, it is not good. Right, so we will try to find the complement. This is the same as 1 minus probability of y. Right, so your value of y, the complement is actually less than or equal to 0. Right, but in your binomial distribution, the smallest value that the random variable can take is actually 0. So we write equal to 0. Right, then it's greater than 0.95. So for the subsequent steps, you make probability of y, taking a value of 0 to be the subject. Right, you'll get it to be less than 0.05. Okay, which is this inequality here. Right, then how do you find this? How do you find this? Okay, this is because you know that, okay, probability of x taking the value of r is given by this equation. Right, so you know that your r here is 0. Right, your p is 0.2. Right, so in this case, you sub in the values of r is 0. This term here will be 1. Okay, this term here is 1. Right, so 1 minus p, right, it is 1 minus 0.2. Right, followed by n minus r. Okay, your n here it is n. Okay, the r here is 0. It gives you n. Okay, so this expression here will give you 0.8 power n. Then you solve as per normal. Okay, you may want to note that when you divide by log of 0.8, there is a change of inequality sign. Okay, because log of 0.8 it is less than 0. Right, then you'll be able to conclude that your n is greater than 13.4. Right, so the least value of n is actually given by 14. Okay, you can also do this using the table method from GC. Right, you can key in your distribution under y1 under the graphical mode. Right, you key in using the parameters here. Right, then you scroll to the table. Right, you see these are answers that is given. Right, you look for the one that has close to 0.5, right, less than 0.5. Okay, this is a value that is first less than 0.5. Right, you are required to give two other values that is next to it, the one before and the one after. Right, and write it in this manner. Right, so for you to be able to do this, you should note that the x here takes integer values. Okay, otherwise this method may not work. Right, so obviously from the table,